In 1917, Einstein suggested that no telescope would ever allow us to glimpse the true edge of the universe. More than a century later, the James Webb Space Telescope's deep fields have reported surprisingly low galaxy counts in certain early universe patches, candidate voids that scientists are still investigating. Could these quiet regions be tied to the limits Einstein warned about, or are they clues to new physics shaping the first galaxies? We'll examine the evidence. This video will explain Einstein's century-old caution about observational boundaries, what Webb actually saw in 2024-2025, why the cosmic microwave background complicates the picture, and how supercomputers and lensing tests aim to resolve the tension. To understand why these questions remain so difficult, we need to revisit how Einstein first arrived at such a stark prediction. Einstein's forgotten prediction. Einstein's forgotten prediction emerged in 1917, when he introduced a way of thinking about the universe that was not common at the time. Scientists of his era were divided. Some described the cosmos as static and eternal, others favored a definite beginning, and a few considered the possibility of constant change. Einstein hesitated to endorse any one view fully. His theoretical work suggested space might expand, but his deeper caution came from something else. He argued that, regardless of whether the universe had a beginning, the very laws of physics might lock away the earliest stages so firmly that no telescope could ever reveal them. This caution did not represent a clear acceptance of the Big Bang. In fact, Einstein's views evolved as evidence developed. He debated competing cosmological models, rejected some, tentatively acknowledged others, and repeatedly returned to the same concern. Even if the cosmos had a definite origin, the physics of those first moments could forever prevent direct observation. Unlike many of his contemporaries who leaned on philosophy or speculation, his restraint was tied to the structure of physical law itself. He recognized that certain conditions would erase records before light was free to spread, conditions that technology could never undo. To explain why he thought observation would fail, Einstein pointed to two fundamental reasons. First, there must have been an epoch in which light, the very carrier of information, could not travel freely. In that era, the universe was too dense and too hot, and photons were trapped within matter. Today, we know this phase ended about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and the cosmic microwave background, CMB, was released. Any attempt to peer farther back with ordinary telescopes, Einstein argued, would strike silence. Second, as space expands, it creates horizons. These horizons mark limits beyond which signals cannot ever reach us. Even if light was emitted, expansion ensures that some regions stay permanently out of causal contact. For Einstein, these two barriers guaranteed that the absolute beginning would remain inaccessible. Modern cosmology has built on this framework. We can describe the CMB with astonishing precision, the glow of the universe when it first became transparent. Yet Einstein's key point remains intact. All events that occurred before this moment are hidden from direct view. The cosmic curtain that existed prior to 380,000 years is not a flaw in our devices, but a fundamental boundary of history. This idea preserves his forecast of a universe with inherent observational limits. This insight carried philosophical weight. If the beginning could never be revealed by light, then cosmological theories about origins would always rest on indirect reasoning, mathematics, models, and traces, but never first-hand images. It was not that Einstein dismissed the possibility of expansion or the idea of a finite origin, but that he suspected the deepest questions would always resist direct confirmation. The universe, in his view, protected its earliest stages behind boundaries no human effort could cross. That caution resonates strongly today. Astronomers continue to refine telescopes, stretch sensitivity, and build instruments capable of detecting ever fainter galaxies. Each leap in technology is celebrated as a step closer to the beginning. Yet Einstein warned of limits set not by engineering, but by the fabric of space and time. Even the ultimate machine, he believed, would find features that could not be explained by mere absence of data, but by the impossibility of access. The implications of that warning have grown sharper as new discoveries emerge. Scientists examining early universe light now compare their results against models that project smooth and nearly uniform density fields. These models are anchored to the CMB, which records the cosmic state just a few 100,000 years after the Big Bang. If Einstein's arguments about natural boundaries were correct, then as telescopes approach these epochs, the conventional picture should become uncertain, perhaps replaced by conditions science struggles to interpret. Einstein's two reasons, photon opacity and cosmic horizons, were not built from modern cosmological detail, but they foreshadowed the most striking constraints we live with today. They outline why the universe retains secrets and why attempts to visualize its birth risk frustration. They remind us that boundaries are not only possible but inevitable. The result is a peculiar tension. We are equipped to see extraordinary detail from billions of years ago, and yet, at a certain point, even our most powerful instruments confront silence. Observers describe this moment as both alluring and unsettling. It is the edge of what nature allows, a ceiling built into reality. This was the sober reminder Einstein left to later generations, that the beginning itself is not an observational target but a permanent horizon. This perspective reshapes how scientists judge new data. What looks like a gap or void may not be a blank left by technology or an error in analysis. It could signal a deeper truth. Perhaps certain patterns cannot appear because they belong to stages of history hidden behind the barriers Einstein outlined. When such gaps emerge in cutting-edge surveys, the question is not simply what is missing, but whether we are confronting the very wall Einstein anticipated. And it is here that present-day results collide with his concern. The most advanced telescope of our time has turned its eyes to the young universe, only to encounter regions where galaxies seem scarcer than expected. Theories predicted gentle, uniform spreads of matter, but instead, astronomers find something unusual. Are these gaps the footprints of physics Einstein warned us about, or do they represent some other unknown process in play? Whatever the cause, these discoveries ensure that his century-old caution continues to guide our interpretation of the cosmos. As the evidence deepens, the stage is set for a surprising problem. Observers expected to see faint galaxies clustering smoothly throughout the first half-billion years of cosmic history. Instead, they confront stretches of remarkable emptiness. The contrast between theory and observation has seldom been sharper, and it forces scientists to reconsider what the early universe was truly like. The strange discovery of primeval voids. The James Webb Space Telescope's 2025 observations introduced a puzzle that astronomers did not anticipate. Instead of only finding the delicate glow of the first galaxies, Webb revealed two surprising trends: unusually bright, mature-looking galaxies appearing at very high redshift, and in some deep fields, large underdense regions, candidate primeval voids, that remain controversial and under review. Webb's data showed an unexpectedly rich population of luminous, little red dots and bright galaxies, but alongside them came reports of significant gaps in the sky where galaxies were scarce. Why is that surprising? Because the cosmic microwave background, our earliest light from 380,000 years after the Big Bang, shows only extremely tiny ripples in density. Structures as large and empty as these should not have emerged so soon. The void detections are based on early results, and researchers emphasize that they will need more spectroscopy and gravitational lensing confirmation before they can be considered secure. Still, what has been reported so far challenges expectations. To see why these findings carry weight, it helps to consider the prevailing model. According to decades of theory, the infant universe began in near uniformity. The tiny fluctuations imprinted in the microwave background would act as seeds, but at first they were no more than 1 part in 100,000 in strength, a subtle gradient in an otherwise smooth fog of matter and radiation. Over billions of years, gravity would exaggerate those tiny ripples, drawing regions together into filaments and sheets and leaving behind vast voids. That is why, when we look at the modern cosmos, we see an intricate web of galaxies separated by cavernous gaps. But in the very first half-billion years after the Big Bang, computer simulations predicted something different. They showed a young universe still wrapped in relative smoothness, with only faint clustering beginning to appear. Against this forecast, Webb's early surveys stand out. Its infrared instruments extend our vision further back in time than any earlier telescope, uncovering faint galaxies that formed just a few 100 million years after the Big Bang. Alongside these galaxies, however, observers noted stretches of sky where light was sparse to non-existent. These were not accidental omissions caused by incomplete imaging. They were consistent across independent fields, implying that in some primordial regions matter was, and perhaps still is, missing. Such underdense zones, if real, seem far too pronounced for a universe at that early stage. The implications reach deeply into cosmology. If vast voids already existed in the first few 100 million years, then either gravitational growth advanced far faster than assumed, or another mechanism drove matter into clumps and left the spaces between unusually barren. In either case, the timeline of structure formation would need correction. Conventional models suggested that the cosmic web took billions of years to mature. Webb's results hint that parts of it were sketched in at the very beginning. Scientists quickly asked whether something more prosaic might be hiding behind the apparent emptiness. Perhaps young galaxies in those regions were unusually faint or concealed behind dust that absorbs visible and infrared light. To test this, researchers examined Webb spectra across multiple wavelengths and compared signals at different depths. The analysis did not restore what was missing. If galaxies exist in those areas, they either emit in ways we have yet to detect, or they are altogether absent. Both possibilities are troubling. The first requires an unknown kind of galaxy invisible to our instruments, while the second forces a radical revision of how cosmic structure assembled. Another layer of contradiction comes from the microwave background itself. Data from satellites like Planck provide exquisite maps of how matter was distributed only 380,000 years after the Big Bang. Those maps reveal differences so fine that they resemble static noise when plotted visually. The path from such delicate ripples to sprawling regions devoid of galaxies after only a few 100 million years appears implausible under standard gravitational growth. The scale and rapidity of the shift push against the boundaries of established physics. Some scenarios have been proposed. Perhaps dark matter behaves differently in the earliest universe, allowing clumps and gaps to form faster than expected. Or maybe the inflationary phase that expanded the universe set initial conditions with stronger irregularities than measurements currently show. Another hypothesis is that interactions in the primordial plasma left certain patches underdense, a feature amplified later on. None of these ideas are more than conjectures, but their discussion underscores how disruptive Webb's candidate voids are. Crucially, these regions do not appear limited to a single direction or survey. Multiple deep fields, chosen across different portions of the sky to avoid bias, each revealed versions of the same pattern, bright galaxy clusters interspersed with noticeably empty expanses. That rules out local coincidence and suggests a more fundamental property of the early cosmos. If the effect survives follow-up scrutiny, voids will have to be accepted as a real feature of the primeval universe, contradicting the smoothness once thought certain. The scale of these reported gaps further heightens the concern. Some span distances that light would take tens of millions of years to travel, a size that seems incompatible with the short time since the Big Bang when they would have emerged. The physics of slow gravitational drift and gradual evolution cannot carve so much emptiness so quickly. To account for such formations, models may need to invoke stronger forces or altered initial conditions. For researchers who have long worked with a framework of gentle, steady growth, the contrast is stark. Still, Webb's findings must be handled with caution. These are preliminary surveys, and some explanations may yet resolve the tension without overturning theory. More spectroscopy is needed to secure galaxy distances, to ensure faint galaxies are not hidden misclassifications, and to test whether gravitational lensing can reveal matter where ordinary imaging sees little. Until then, the voids remain a candidate phenomenon rather than a confirmed fact. But even as candidates, they provide a striking reminder that the deeper we look, the more unsettled our assumptions become. In this sense, the telescope's revelations echo a warning voiced long ago. Einstein argued that nature would place boundaries on direct observation of the beginning. While the empty patches Webb reports are not identical to those boundaries, they push us closer to edge conditions where observation may blur into silence. They remind us that the early universe may not appear in the tidy, uniform patterns that textbooks predicted, but in ways that highlight how limited our reach might be. In confronting these voids, science faces a choice: interpret them as cracks in the standard picture of galaxy formation, or treat them as subtle clues pointing to a deeper constraint built into the history of light itself. Either way, the reported emptiness stands as a puzzle not yet resolved. And to understand whether these mysteries truly reflect nature or only illusions of observation, we need to turn back to an even older chapter in cosmic history, a span of time when no galaxies shone at all, and the universe itself fell silent. The Dark Ages of the universe. After recombination, about 380,000 years after the Big Bang, the universe entered what scientists now call the Dark Ages. At that moment, protons and electrons combined into neutral hydrogen, ending the hot plasma state that had trapped photons since the beginning. The cosmos became transparent for the first time, but with no stars or galaxies yet burning, there was no fresh light for telescopes to collect. The only radiation filling space was the faint afterglow of recombination, which in our time is seen as the cosmic microwave background. For any future observer, this created a natural boundary. Classical telescopes can observe only photons, and before this transition, there are no photons escaping to form an image of earlier events. Einstein anticipated this wall of silence decades before physicists formalized it. His reasoning was not about technology, but about limits built into the fabric of physics. He warned that no matter how advanced an instrument became, it could never recover signals that never existed to begin with. Light before recombination was trapped, and past that threshold, there is nothing for optics to detect. This insight aligns exactly with the Dark Ages, a period when physics, not engineering, drew the line of observational reach. The conditions during this era were unusual by later cosmic standards. Hydrogen and helium dominated, spread almost evenly through expanding space. Gravity had already begun pulling regions together, but at first it created only faint overdensities. These small clumps did not shine. They did not yet host stars or black holes. The physics of the Dark Ages was active. Matter cooled, dark matter gathered, chemistry slowly progressed, but all of it was invisible in photons. In practical terms, it was a silent economy of structure that stayed hidden, because sight itself depended on light that had not been released. Although 380,000 years might sound short compared with the present age of the universe, it was an extended span in the early timeline. As the universe expanded, the wavelengths of the cosmic afterglow stretched into ranges far beyond visible light. Today that glow appears to us only as a microwave signal, measured with specialized instruments far more sensitive than any ordinary telescope. Aside from that background, nothing reliable crossed space until the first luminous objects ignited hundreds of millions of years later. For astronomers, this silence means that attempts to look earlier with light-based instruments are impossible. No aperture, whether in space or on Earth, can recover photons that never broke free. This makes Einstein's early caution remarkable. At a time when expansion models were being debated, he identified a principle. There are epochs in cosmic history inherently closed to direct observation. Later science gave this stage a name, the Dark Ages, but Einstein had already insisted that such a gap must exist. It was not simply a technical obstacle, like noise introduced by Earth's atmosphere or limited sensitivity. It was a conceptual boundary imposed by the physics of light itself. The Dark Ages illustrate that principle vividly. Scientists comparing Webb's results to these predictions have raised a provocative thought. Could some of the reported voids, the underdense regions appearing in its deep fields, echo this ancient silence? Perhaps what seems like missing matter in the young universe is, at least in part, an imprint of phases when light was absent rather than structures entirely gone. Within the first few 100 million years, the cosmos was still shaped by darkness, and galaxies had only begun to emerge. Einstein's curtain may not only apply to epochs far before recombination. It might resonate as faint signatures even in the territory Webb explores. It is important to note that the Dark Ages did not end sharply. Instead, the gradual appearance of the first stars and black holes lit small, scattered zones of ionization. Slowly, ultraviolet light from these objects began breaking apart the neutral hydrogen around them, slicing open corridors of visibility. This long and uneven transition is known as reionization. Over hundreds of millions of years, it expanded, transforming the universe into a luminous environment where starlight and radiation flowed freely through space. Only after reionization had progressed could light-driven observation illuminate the large-scale structures we detect today. Webb's design specifically targets this threshold. By detecting faint, redshifted infrared signals, it looks as far back as possible, close to the end of the Dark Ages. Some of its youngest observed galaxies sit right on that boundary, flickering at the start of cosmic dawn. They serve as markers of an edge, signposts that visible structures had finally begun to form. But Webb does not break into the Dark Ages themselves. Its mirrors and detectors cannot reveal the actual silence of the earliest period, because no photon image was left behind from that time. In this respect, Webb confirms Einstein's warning. The most powerful optical telescope in history still collides with the same fundamental limit. Webb's deep infrared imaging pushes back as close as possible to the end of the Dark Ages, but it cannot reach the literal earliest epoch that Einstein worried about. This does not diminish the telescope's discoveries. Instead, it clarifies the stakes. When we perceive gaps or voids in its pictures, we must remember they may not always represent errors in theory or missing data. Sometimes, they reflect natural silences built into the cosmos, shadows created not by absence but by physics itself. The Dark Ages remind us that vast stretches of cosmic history, though real, have no visible record. Such intervals will always look like emptiness when we try to view them with light. And so the consequences extend into interpretation. Observers may understandably be unsettled by striking voids glimpsed in Webb's early universe fields. But in light of the Dark Ages, such outcomes could align with expectation rather than contradict it. In the broadest sense, the universe has been consistent. Where there is no light, there will be no image. Einstein's warning about locked horizons appears not as speculation, but as a lived boundary of astronomical practice. The lesson is that searching farther and deeper is not the same as always finding more. In some cases, looking beyond a certain limit reveals only the limits themselves. To understand this better, scientists turn to the one remnant that actually does survive from before starlight began, the background glow left at recombination. Unlike galaxies or voids, this signal pervades every direction, an ancient radiation frozen into the sky. It carries a message about the earliest stages, not in brilliant images, but in faint patterns that still whisper today. When background radiation speaks. When astronomers in the 1960s encountered a faint, omnipresent radiation in their instruments, they realized they had uncovered the fossil light of the young cosmos. This discovery became known as the cosmic microwave background, or CMB. It was neither the glow of stars nor the light of galaxies, but the leftover radiation released when the universe cooled enough for neutral atoms to form, about 380,000 years after the Big Bang. Before that stage, photons could not travel freely, but at recombination, the universe became transparent, and light began its long journey across expanding space. By the time it reaches us today, its wavelengths have stretched into the microwave range. Although imperceptible to the human eye, it surrounds us in all directions, a subtle background imprinted with invaluable information. From the moment it was detected, the CMB provided scientists with a direct record of the early universe's structure. Satellites such as COBE, WMAP, and Planck charted this faint light across the entire sky, uncovering minuscule temperature variations. These fluctuations amount to differences of only a few hundred thousandths of a degree, yet they revealed where matter and energy were slightly denser or more rarefied. Over time, these tiny imbalances would grow into galaxies, clusters, and the vast cosmic web. Each new generation of data refined the levels of precision and allowed cosmologists to test inflation, measure curvature, and estimate the proportions of dark matter and dark energy. By 2025, the most recent measurements pushed this even further, combining sophisticated ground-based observatories with updated space-based analysis. Critical updates came from the Atacama Cosmology Telescope in Chile and the South Pole Telescope's third-generation survey, SPT-3G. Results released in 2024 and 2025 have sharpened constraints on parameters such as the density of dark matter, the tilt of the primordial spectrum, and the expansion rate of the early universe. These findings overwhelmingly support the standard Lambda CDM model, reinforcing that inflationary expansion and dark energy remain the best explanations of the data. Yet, they also highlight one of the most stubborn, unresolved issues: the Hubble tension. CMB-based estimates of the Hubble constant give a value around 67 to 68 kilometers per second per megaparsec, while local measurements using supernovae and other techniques consistently point closer to 73. The updated ACT and SPT maps strengthen the CMB side of the equation, which means the discrepancy has become sharper, not weaker. This dual role, the CMB confirming the broad strokes of cosmic evolution while leaving a persistent mismatch on key measurements, frames today's debates. On one hand, the background signal provides a coherent, internally consistent picture of the early density field. On the other hand, Webb's reports of primeval voids appear starkly at odds with it. The CMB's fluctuations at recombination are exceedingly mild, like ripples on a nearly flat lake. Standard gravitational growth over the first few hundred million years could not stretch those ripples into immense voids. This is not to say the CMB proves large gaps could not exist, but rather that the physics connecting recombination to the first galaxies does not naturally generate such extreme structure on such short timescales. That clash is what makes Webb's tentative void findings so difficult to reconcile. To understand why the CMB story is so constraining, it helps to picture it as a photograph of the universe's surface at 380,000 years old. The features visible in that photograph are variations in density totaling only tiny fractions of a percent. Gravity has had nearly 14 billion years to amplify them into today's immense cosmic web, a transition well modeled by Lambda CDM. If those models are correct, then halfway through the first billion years, the universe ought to appear gently modeled, small galaxies forming but arranged without vast empty expanses. Webb, however, suggests the presence of significant underdense zones far earlier than theory would allow. Thus, the comparison of early light with later snapshots forces cosmologists to ask what might be missing from the framework. The most recent CMB measurements also provide detailed polarization maps. These patterns encode information about how photons last scattered during recombination, effectively retaining a record of primordial sound waves in the plasma. These oscillations, known as baryon acoustic oscillations, can be traced in both the CMB and in today's distribution of galaxies. They follow a regular scale that acts as a cosmic yardstick. Yet where the oscillations predict moderate clustering, Webb's candidate voids point to more pronounced separation. In this sense, the oldest radiation and the newest telescopes seem to be telling slightly different stories, one of steady, ordered growth, and one of abrupt gaps that theory struggles to explain. Part of the complication comes from what the CMB cannot show. Its photons originated only after recombination, so it cannot preserve any direct trace of what happened earlier. The plasma before that epoch was opaque, preventing any radiation from carrying information forward. This means that while the CMB is the oldest light we can detect, it does not offer a literal picture of the universe's origin, only of conditions at a later boundary. Einstein's warning about built-in observational limits takes on substance here. Light cannot reveal the stages before photons had freedom, no matter how refined our detectors become. In that respect, the CMB functions more like a fossil than a living view. It encodes evidence of temperature variations, density fields, and acoustic oscillations that underpinned later structure, but it cannot reconstruct the origin itself. Even the newest maps, precise to a few millionths of a degree, remain silent about what occurred before recombination. They describe physics at a boundary, but provide no direct window to what came before. The silence is not technological but intrinsic. This quality helps explain why the CMB both anchors and limits cosmology. It confirms that the universe was remarkably uniform, with only minute deviations, and it anchors the Lambda CDM framework. But its universality also obscures specific details. The CMB fills the sky uniformly, but it conveys no sharp view of individual voids or galaxies. It can only provide statistics, not images. Instruments like Webb, by contrast, deliver localized pictures of early structures. When those pictures reveal features that seem too dramatic for the CMB's mild pattern, the tension becomes unavoidable. The result is a scientific paradox. The background radiation remains the most robust measurement we have, consistently reaffirmed by Planck, ACT, and SPT. It depicts a universe coherent with inflationary beginnings and steady growth. At the same time, telescopic surveys point toward anomalies that appear inconsistent with that calm foundation. Scientists know the CMB story is valid within its domain, but they must ask whether additional processes between recombination and reionization altered the pace or scale of structure development. Even so, one theme is clear. The CMB has affirmed its role as the primary anchor for early universe physics. If voids of surprising scale do emerge in Webb's maps, then explanations will have to reconcile them with the underlying density field seen in the CMB. That might mean rethinking parts of gravitational growth, considering interactions of dark matter more seriously, or revisiting assumptions about baryonic feedback in early epochs. But any model must still fit with the precise constraints now set by ACT and SPT. Einstein would likely have noted the irony. The most sensitive measurements of the cosmos still tell us what cannot be seen, even as they reveal immense detail. Radiation from the early sky places a wall before origin questions, while new telescopes raise challenges from within later epochs. Together, they build a sharper picture, but also a sharper contradiction. This contrast makes the next puzzle more pressing. If the CMB records only gentle ripples, but Webb observes dramatic underdensities, what about the galaxies themselves that appeared astonishingly early? They offer a different kind of surprise, forms of structure that should have taken far more time to assemble. Galaxies that shouldn't exist. When the James Webb Space Telescope began returning its deepest images, astronomers noticed something beyond faint smudges of newborn light. Among the expected fragile structures of gas, Webb revealed surprisingly bright and massive galaxies appearing only a few 100 million years after the Big Bang. Some were cataloged in the JADES survey, JWST Advanced Deep Extragalactic Survey, others in the CERS program, Cosmic Evolution Early Release Science, and still more in a University of Missouri-led study that flagged over 300 candidates. Observers also pointed out the so-called little red dots, compact sources whose luminosity and color hint at rapid star formation or buried black holes. Taken together, these findings unsettled a framework that predicted sparse, irregular clumps rather than galaxies of such scale and maturity so soon after the universe's beginning. According to established cosmology, the earliest galaxies were expected to grow gradually within dark matter scaffolding. Small gas clouds would collapse, form primitive stars, then merge step by step, eventually accumulating into larger systems. The first few 100 million years were supposed to be turbulent and inefficient, marked by scattered knots of star formation easily disrupted by feedback from supernovae. But Webb's surveys at redshifts corresponding to 300–500 million years after the Big Bang displayed objects with luminosities and stellar masses rivaling those of dwarfs in the modern universe. Instead of disorganized beginnings, observers saw coherent galaxies shining with billions of stars. Spectroscopic data made the picture more striking. The light from some of these systems carried signatures of stellar populations already several 100 million years old. If confirmed, that would mean star formation ignited far earlier, perhaps within the first 200 million years of cosmic history, well before prior models permitted. Earlier expectations had been that population III stars, consisting only of hydrogen and helium, would burn briefly, explode, and enrich space with heavier elements. Only after multiple such cycles should larger, metal-rich galaxies emerge. Webb's candidates appear to condense that process, bypassing the long preparation stage and presenting stellar maturity well ahead of schedule. The inferred sizes of some galaxies compound the problem. Several candidates exhibit stellar masses multiple times greater than allowed by simulations of early structure. Instead of systems, only a fraction of the Milky Way's satellites. Webb identified galaxies with billions of solar masses in stars alone. Standard estimates, based on fluctuations seen in the CMB and accepted collapse rates, limited what should reasonably exist in that era. To build galaxies on this scale, matter had to concentrate vastly faster, or through mechanisms not yet described by current cosmology. Astronomers proposed comparisons to illustrate the mismatch. It would be as though complex civilizations appeared almost immediately after humanity evolved, skipping millennia of gradual cultural buildup. In the same way, galaxies emerged in apparent contradiction to cosmological schedules. Researchers began questioning whether star formation was more efficient under the high-density conditions of the early universe, or whether dark matter influenced collapse in ways not anticipated. Others speculated that extreme energies or direct collapse black holes anchored the rapid assembly. Each scenario offered possibilities, but none yet fit seamlessly with existing models. Naturally, scientists asked whether Webb might be tricking them with misclassified imposters. A galaxy could appear much farther if dust reddened its light, creating the illusion of distance. Yet spectroscopic follow-up for several key systems confirmed that their redshifts were real, placing them squarely within the early epochs. These galaxies are not simply nearby objects disguised by dust. They occupy the same period immediately following the Dark Ages. That confirmation shifted discussion from technical error to theoretical consequence. Webb's optics were not making mistakes. The timeline of structure itself requires rethinking. Still, some caveats remain. Spectroscopic confirmation matters. While a number of early galaxies have secure redshifts from JWST's NIRSpec and ground-based follow-ups, many of the brightest and most controversial candidates remain photometric estimates. Until spectroscopy backs them, their distances are less certain. Researchers caution that conclusions must rest on the best confirmed subset and await verification of the full sample. In the face of apparent contradictions, theorists began searching for explanations that could reduce the tension. Some noted Webb's infrared sensitivity exceeded original expectations, making it more effective at capturing faint but distant light than models assumed. Others pointed out that early galaxies Webb imaged could be rare peaks, statistical outliers in a universe that overall matched models better. Feedback may also be less disruptive than once thought, with stars forming in short, bursty episodes compact enough to boost luminosity without requiring extreme mass. Finally, some little red dots may actually be powered by overmassive black holes, masquerading as unusually large galaxies. These combined explanations help reconcile the first wave of claims, but do not resolve all discrepancies. Even with such refinements, the sheer consistency across Webb's fields remains hard to dismiss. In survey after survey, astronomers encountered luminous galaxies at high redshift. The prevalence suggests these are not isolated rarities. Instead, something systemic may have shaped the early universe toward faster or more efficient growth than anticipated. The repeated appearance undermines any perception that the first galaxies seen were flukes of observation. One way scientists frame the issue is with compressed time. Processes assumed to take billions of years seem concentrated into the first few 100 million years. The mechanics of collapse, how quickly gas cools, how radiation pressure halts contraction, how supernovae eject material, set firm boundaries in conventional models. For those processes to be compressed so dramatically, they require either overlooked efficiencies or new physics. This challenge has spurred massive computer simulations, but producing results that match Webb's observations has proven remarkably difficult. The gap between theory and measurement persists. The presence of mature galaxies in cosmic dawn complicates the broader picture drawn from other data. On one side, the CMB fixes initial density fluctuations at very modest levels. On another, Webb reports candidate voids where galaxies appear absent. And alongside both, these compact yet luminous systems suggest runaway growth far earlier than expected. All three, CMB ripples, early emptiness and robust galaxies, together spotlight contradictions in the first billion years of cosmic history. Something in the transition from uniform plasma to structured matter fails to align with received theory. Instead of discouraging researchers, these findings have opened new avenues of inquiry. The galaxies detected by Webb illustrate that nature assembled coherent structures under conditions thought far too short and turbulent. They force reconsideration of how matter collapses, how cooling proceeds, and how black holes might anchor growth. They encourage re-examination of ideas about baryonic physics, stellar feedback, and exotic dark matter scenarios. Whatever the explanation, it is clear that the timeline of structure formation cannot be mapped as simply as once believed. This tension highlights an important next step. If galaxies appeared early and voids also loom at unexpected times, then a unifying factor must influence both the crowded and the empty. Astronomers now look toward the underlying scaffolding that shapes matter, seeking whether an unseen framework may explain why galaxies emerge so fast in some regions, yet remain absent in others. The invisible hand of dark matter. In every modern description of cosmology, dark matter is treated as an unseen actor shaping the evolution of the cosmos. It emits no light and absorbs none, yet its gravitational pull sculpts the patterns into which ordinary matter falls. Stars, gas, and galaxies form within the wells created by this hidden material. Without dark matter, galaxies would never have gathered into coherent systems, and the cosmic web would not exist in its immense, interconnected form. When astronomers now confront reports of large underdense regions and unusually mature galaxies in Webb's early universe surveys, the discussion inevitably circles back to dark matter, since its distribution sets the stage on which luminous matter appears. or fails to appear. The very idea of dark matter originated from a simple inconsistency in motion. Galaxies rotate too quickly for their visible stars to remain bound under Newtonian gravity alone. Something unseen adds mass to those systems, keeping them intact. Over time, this mystery grew into a foundation of cosmology. Surveys of galaxies revealed coherent filaments, immense clusters, and expansive voids, patterns of structure too strong to arise from visible matter alone. Dark matter provides the gravitational backbone of this network. Cosmic gas and dust streamed toward that skeleton, cooled, and began forming the stellar islands we observe today. In this sense, cosmologists describe dark matter as the scaffolding of the universe, present but invisible, directing how cosmic growth unfolds. Placing this idea into the early epochs now probed by Webb raises pressing questions. If the telescope records unusually empty patches while other regions host galaxies far too massive for their time, perhaps the culprit is not luminous matter, but the behavior of dark matter itself. In theory, dark matter should be smoothly distributed at first, perturbed only by tiny fluctuations seen in the cosmic microwave background. Yet Webb's findings hint at stronger contrasts developing far sooner. This opens the possibility that dark matter clumped more quickly in some regions while remaining diffuse in others. Luminous galaxies would then assemble in dense zones early on, while other areas stayed barren, appearing to us as primeval voids. Direct evidence for dark matter in these formative stages is hard to capture, but researchers have begun to assemble it from independent studies. For example, observations with the Atacama Large Millimeter/Submillimeter Array, ALMA, have detected ionized carbon emission, C+, from the gas surrounding some of the earliest known quasars. These signals trace massive dark matter halos enveloping galaxies less than 1 billion years old. The presence of such vast halos demonstrates that dark matter was already central to the growth of the first luminous systems. It reassures astronomers that the invisible framework truly existed then, and it sets a precedent for looking to dark matter when interpreting Webb's anomalies. If those halos shaped early quasars, similar unseen concentrations could also explain why galaxies flourished in some regions yet failed to appear in others. Yet speculation must be handled carefully. Some researchers have suggested the idea of dark galaxies, systems where dark matter dominates, but where little or no starlight has ever formed. Such structures could sit inside regions now seen as empty, invisible to telescopes tuned only to light from stars. But because dark galaxies shine so weakly, detecting them requires indirect methods. The most promising tool is gravitational lensing. When the light from even more distant galaxies travels past a massive, dark object, it bends, distorts, or magnifies. By carefully measuring this lensing effect, astronomers can estimate how much unseen mass lies along the line of sight. Applied to regions where Webb sees emptiness, lensing could reveal whether dark structures exist there. This approach is already being attempted. Lens mapping in 2025 across several candidate voids has produced a mixed set of results. Some regions show very weak lensing, consistent with genuine underdensities of both dark and luminous matter. Others show signals suggesting hidden concentrations of mass that simply lack stars. Combined studies, using Webb's high-resolution imaging alongside ALMA and ground-based lensing programs, aim to clarify whether these zones are truly empty or only appear empty because their mass is dark. The early verdict is cautious. Dark matter remains a prime candidate for shaping uneven early structure, but current observations provide mixed signals. Astronomers emphasize that more lensing analysis and spectroscopic follow-up are essential before drawing strong conclusions. Several hypotheses explore how dark matter might behave differently in early times. One suggestion is that it cooled or collapsed rapidly in some regions, producing concentrated halos that accelerated galaxy growth. Gas falling into these wells could ignite stars far sooner, explaining Webb's surprisingly mature galaxies. Surrounding areas where dark matter remained diffuse would produce void-like regions. Another speculative line proposes multiple species of dark matter particles with varied clustering behavior. Some types could have collapsed early, while others resisted structure, leading to contrasts in density. These scenarios would generate the balance of crowded and empty regions now appearing in Webb surveys. Still, such ideas remain conjectural until further evidence appears. Alternative explanations cannot be ruled out. Apparent voids may arise in part from projection effects, where overlapping distributions at different distances confuse the pattern. Dusty galaxies, faint enough to be missed in some imaging filters, might also hide inside underdense zones. But the fact that large gaps appear across multiple fields weakens the argument that coincidence alone is at play. Whether the result is true underdensity of both matter types, or darkness hiding as yet unlit halos, the possibility that dark matter plays an uneven role across early epochs remains on the table. To test these options, researchers lean heavily on large-scale computer simulations. Cosmologists have modeled universes with cold dark matter, warm dark matter, and interacting variants. Each produces different void distributions and halo properties. Comparing these prints against Webb's maps is ongoing. At present, the cold dark matter model that underpins lambdacdom has trouble matching both the speed of massive galaxy formation and the scale of such early voids. Some non-standard variants come closer, but no simulation yet captures all the observations. This mismatch is why the debate remains unsettled, and why dark matter continues to be both the most necessary and the most elusive part of the solution. Dark matter accounts for most of the universe's matter content, yet no instrument has yet detected it directly. Telescopes see only how it shapes the behavior of everything else. Its silence in light is the reason gravitational lensing is indispensable. Its dominance explains why voids and early galaxies cannot be understood without considering it. If the underlying distribution of dark matter set the pace of structure, Webb's surprising discoveries are signals of that invisible hand. But dark matter may not answer everything on its own. Current evidence shows that while it is likely part of the cause, it is not yet a complete explanation. In the broader view, this enigma aligns with an old warning. Physics can sometimes reveal not just what exists, but what will remain permanently hidden from us. Even the most powerful tools may run into boundaries imposed by nature, not by technology. Dark matter's invisibility is one expression of this, and the possibility that true cosmic voids already existed so early sharpens the paradox. The cosmos appears to retain both luminous structures and profound silences that resist straightforward explanation. There is, however, another limit at play beyond the unseen mass. Einstein proposed that even if new tools unveiled extraordinary structures, there would always be horizons, edges enforced by the expansion of space itself. That expansion, he argued, conceals the beginning forever beyond observational reach. Einstein's expanding horizon offered a second reason why the earliest moments of the universe might remain forever hidden. He recognized that as space enlarges, it drags the limit of what we can possibly observe along with it. The universe does not present a fixed edge that waits for us to reach it. Instead, the boundary itself recedes, carried outward by expansion. This suggested that any deeper attempt to look back in time would meet not with a solid wall, but with a retreating horizon. From the equations of general relativity alone, he understood that the fabric of spacetime itself ensures that some regions, even if they are real and filled with matter, can never send us light. To picture what Einstein meant, imagine standing on the shore while watching a ship move out to sea. If the boat sails faster than you can swim, the distance between you and it will always increase, no matter how much effort you put in. In cosmology, the swimmer is light, and expansion is the boat accelerating away. Photons from the earliest structures begin their journey, but as they travel through an expanding cosmos, their wavelengths are stretched and their energy diluted. The measure we call redshift records this effect. At modest redshifts, the signals reach us, though weakened. But beyond a certain scale, the expansion moves them faster away than their photons can progress forward. That threshold defines a horizon, a moving limit that lies within the laws of physics, not within our technology. This limit is referred to by cosmologists as a particle or event horizon, the maximum distance light could have traveled to us since the Big Bang. Observations of supernovae and the CMB have clarified that expansion is not only present but accelerating, a phenomenon described as dark energy. This acceleration makes the horizon particularly severe. Expansion creates the horizon, but accelerated expansion intensifies its retreat. The faster the fabric of space grows, the faster the observable boundary races away from us. Einstein did not know the details of dark energy, but his insight foreshadowed exactly this combination. Expansion sets a barrier, and acceleration reinforces it. Redshift also provides a practical demonstration of this principle. Webb sees infrared light because the glow of early galaxies has been stretched beyond visible wavelengths by expansion. At higher redshifts, photons are lengthened into the microwave or radio regime. Beyond that, signals are flattened into noise no detector can recover. The fundamental limit appears not because instruments lag in sensitivity, but because expansion erases the information on its way. This is Einstein's horizon. No photon from certain epochs will ever arrive, regardless of what technology we build. To maintain a sense of scale, we can currently reach back with photons only as far as the cosmic microwave background, about 380,000 years after the Big Bang. With JWST, we observe galaxies as early as just 300 million years later, impressive progress but still constrained by the horizon. Anything earlier than recombination cannot be seen in photons at all. This simple number, 380,000 years, illustrates that a true origin view is permanently hidden, with the horizon set by physics itself. Present observations confirm the horizon's practical effects. The observable universe now has a radius of around 46 billion light-years, much larger than its age in years, because expansion has stretched the intervening space. Galaxies Webb observes at redshift 13 or more are not seen as they are today, but as they were almost 13.5 billion years in the past. Their present-day states are already shifted far outside our particle horizon, lost to direct observation. This is why astronomers emphasize that the observable universe is not the entire universe. It is only the part whose light had time to reach us. It is essential, however, not to mistake this boundary for an explanation of Webb's observational surprises. Expansion sets limits on what we can see, but it does not on its own cause large primordial voids. The underdense regions Webb has reported remain empirical puzzles demanding astrophysical causes or new cosmological physics. Expansion describes why sight stops at a horizon, not why certain visible fields appear emptier than models expected. Einstein's horizon explains the boundary of observation, not the absence of galaxies where light truly does reach us. Expansion also changes the way we interpret the cosmic past. Every redshifted photon arriving today maps to an event billions of years old. When we detect high redshift galaxies, we are not looking across space alone, we are looking back in time. At low redshift, the difference between spatial distance and look-back time is modest. At very high redshift, the difference is dramatic. This means an image at the edge of visibility is less like a present snapshot and more like a fossil. What looks like proximity in time is in fact billions of years older. The horizon enforces that there will always be a final limit to how much past we can recover. The accelerated phase of expansion complicates this picture further. Evidence from supernova surveys, the CMB and baryon acoustic oscillations shows that in the last few billion years expansion has sped up under the influence of dark energy. This acceleration stretches the cosmic fabric faster than it once did, and with it, the horizon retreats even more decisively. The effect is that while we continue to build sharper telescopes, the distance to the absolute boundary expands faster than any advance in sensitivity. In principle, we are forever chasing an edge that itself will never stop fleeing. Understanding this has become central for astronomers when they interpret Webb's deepest images. A galaxy at redshift 13 is not just a data point on a chart. It represents a position right up against the horizon, a marker of how far photons could travel before being overtaken by expansion. Beyond that lies unobserved territory. Galaxies likely do form there, stars burn and processes unfold, but their signals will not reach us. The horizon blocks them in principle, not in practice. This creates a clear separation in thought. Some parts of the universe we can measure directly. Beyond that, theories cannot be empirically tested by photons. Einstein's view therefore stands. Horizons are not set by engineering but by spacetime. His concept of a receding limit reminds us that science is bounded, not only by what we can build, but also by what the universe permits. Every measurement Webb returns confirms this reality. The signals of young galaxies stretch across space to arrive, but none from truly primordial moments will ever pass through the horizon. The event horizon of expansion is woven into the architecture of the cosmos. This realization has implications far beyond technical astronomy. It means that the dream of seeing the absolute beginning directly is not only impractical but unavailable. The horizon transforms the origin into a concept detectable only through indirect evidence, never through direct light. Even as Webb rewrites textbooks about galaxies forming early and structures appearing sooner than expected, its discoveries take place within this larger truth. No image will capture the true beginning. Expansion governs what astronomy can retrieve and redraws our ambitions within that boundary. For cosmologists, the horizon also forces humility. Every discovery near redshift 10, 12, or 14 reminds us that we are pressing against a shifting wall. Each photon lies at the limit of what can exist in a visible record. Beyond that edge may lie further variations, hidden galaxies, massive halos, or entirely new phenomena that we can reason about but never see. The ongoing acceleration ensures the list of unseen domains grows rather than shrinks. No matter how precise our instruments or advanced our models, some questions remain outside the horizon's reach. And this sets the stage for deeper uncertainties now confronting Webb's community. If expansion places clear and unbreakable limits on how much past can be recovered, then how should we think about regions within view that still appear strangely vacant? When emptiness shows up where light should reach us, we are no longer dealing with the cosmic wall, but with phenomena inside it. That distinction invites a more difficult question. What should we make of stretches of sky that seem to contain almost nothing at all? The question of true nothingness. When early Webb images reported regions where galaxies seemed absent, astronomers raised a difficult question. Are these places genuinely empty, or are they filled with matter that eludes present detection? This is the central issue of the so-called question of true nothingness. Physics has long shown that space is rarely, if ever, an absolute void. Even the sparsest intergalactic expanses today still contain diffuse atoms, stray photons, magnetic fields, and the gravitational pull of dark matter. If Webb's darkest patches represent something more than a lack of visible galaxies, then they may be windows onto forms of structure or energy that our instruments cannot yet register. The distinction is crucial. A zone truly barren of all matter would amount to an absence in creation itself, while a hidden layer of matter or energy would instead reflect the limitations of light-based observation. The first speculative possibility is that some of these areas might host dark galaxies. In this idea, matter did clump in those regions, but with little or no star formation. Without starlight, these galaxies would remain invisible to Webb. The only hint of their presence would come from their gravitational influence on light passing behind them. Gravitational lensing becomes the essential test. If dark galaxies lurk inside these gaps, light from still more distant sources should bend, distort, or magnify as it passes through. Beyond lensing, ALMA has already provided a way to search for early hidden structures by mapping submillimeter signals such as ionized carbon C+ from quasar host galaxies, which trace dark matter halos that do not shine directly. But the lensing results across Webb's candidate voids are inconsistent. In some regions, little lensing appears, consistent with genuine underdensity. In others, subtle distortions hint at mass we cannot see. This leaves dark galaxies as a speculative but testable option, though not yet verified. A second, far-reaching hypothesis considers whether visible voids could be scars from interactions with space outside our observable patch. In theories of eternal inflation, multiple bubble-like universes could exist, and occasional collisions between them might leave traces, circular patterns in the CMB, unusual alignments, or areas where ordinary structure failed to develop. A collision of this kind could, in principle, suppress galaxy formation over a large patch, mimicking a primeval void. Yet this remains highly speculative. No clear evidence has tied Webb's reported underdensities to such collisions, and current methods have not established any concrete multiverse signature. Researchers often present this hypothesis as a theoretical boundary marker rather than a practical explanation. For now, discussion of multiverse collisions reflects curiosity about extreme possibilities more than it offers a real path forward. Quantum physics offers another avenue of speculation, centered not on alternate universes but on the vacuum itself. In quantum field theory, empty space is never truly blank. Instead, it hosts virtual particles blinking in and out of existence, and subtle energy shifts that can even be measured in experiments, the Casimir effect being a laboratory example. On cosmic scales, this constant activity supplies vacuum energy, often associated with dark energy, and may vary across regions. If vacuum properties behave differently in some patches of the early universe, they could have nudged matter away or altered the growth of structure, leaving behind swaths that appear empty to photon-based telescopes. Such a scenario would not mean nothingness, but rather zones dominated by hidden energy fields. While intriguing, this too remains speculative and would require independent signatures, either from cosmological surveys or from particle physics experiments, to move beyond theory. For now, it is a reminder that even the vacuum carries structure invisible to Webb. Some caution is necessary when weighing these proposals. Many researchers emphasize more conservative checks before invoking radical physics. Instrumental biases, incomplete spectroscopic confirmation, or astrophysical processes such as dust blocking light could exaggerate the apparent scale of emptiness. In practice, Webb's candidate voids must survive multiple layers of scrutiny, from deeper imaging to independent surveys and cross-checks with other background signals. This is why current focus has shifted toward practical tests, high-resolution lensing maps, extended spectroscopy to confirm redshifts of faint galaxies, and correlation with CMB data that set initial density conditions. Only after these careful steps can scientists know whether voids really demand exotic explanations or whether overlooked astrophysical variations produce the effect. Even accepting this focus on caution, the philosophical weight of the problem remains. The term void suggests utterly empty space, but physics does not allow true emptiness in that sense. Spacetime itself is a presence, stretching and curving under the weight of mass energy. Every void is filled with that fabric, and in most models it also carries dark matter and dark energy as unseen foundations. What Webb calls empty may therefore indicate not nothing but silence, regions where no light has broken free to signal what lies within. This silence, if verified, would represent the kind of natural barrier Einstein anticipated, a feature created by physical law rather than human error. This ambiguity unsettles cosmologists because each speculative answer remains incomplete. Dark galaxies lack definitive detection. Multiverse collisions inspire models but lie beyond current testing. Quantum vacuum effects could play a role, but no one has tied them directly to Webb's observations. The paradox is sharp. A standard Lambda CDM model predicted smoother early structure than what void reports imply, yet the boldest new explanations exceed the boundary of practical measurement. Researchers find themselves between an incomplete conventional picture and proposals that stretch far ahead of available evidence. Another reason these gaps matter is that history shows voids often become milestones of discovery. Interstellar space was once thought featureless, until thin gases, cosmic rays, and magnetic fields were found streaming through it. Intergalactic space seemed empty until dark matter and dark energy were revealed to dominate its contents. Each time, perceived nothingness turned into hidden structure. It is possible that Webb's reported voids continue this tradition. What registers as blank today may yet prove crowded with phenomena that instruments cannot currently reveal. The lesson is that cosmology rarely leaves true nothing untouched. Instead, apparent absence usually signals overlooked presence. For now, the evidence leaves the balance unresolved. Webb's deep fields show patches poorer in galaxies than expected, but their status remains uncertain pending spectroscopic confirmation and improved lensing data. Conservative explanations, like faint galaxies hidden below detection thresholds, compete with more speculative visions drawn from dark galaxies, altered vacua, or cosmic bubble collisions. None yet close the contradiction with confidence. All that can be said with certainty is that the gaps are real in imaging data. They are larger than the neatest models predicted, and they pose questions not easily set aside. Whether the darkness truly conceals matter or represents a deeper misfit in theory, the possibility that what appears as nothing is something unaccounted for continues to guide the debate. The task moving forward will require tools other than speculation. Scientists need methods that can stretch beyond the photon-based boundaries Einstein identified, without breaking into fantasy. The most promising avenue today is not a theoretical leap into unseen universes, but a practical advance, running new generations of simulations so thorough that they can test whether known physics can reproduce what Webb records. To face the puzzle of supposed nothingness, cosmology increasingly relies on efforts that Einstein himself never could have foreseen. Machines designed to recreate entire universes inside their circuits. The role of modern supercomputers. Modern cosmology now depends on the most powerful computers ever built, systems designed to process numbers at scales beyond what any researcher could perform alone. These are not everyday machines. They are exascale supercomputers, capable of carrying out quintillions of calculations per second. Alongside them, quantum-based processors are starting to take shape, replacing certainty with probability and exploring physical interactions in ways traditional algorithms cannot. Together, they provide cosmologists with essential tools to test whether known laws can explain the universe that Webb, Planck, and ground-based observatories are revealing. The purpose is straightforward but enormous: to see whether gravitational growth, dark matter scaffolding, and feedback from stars and black holes can, under certain assumptions, recreate galaxies and voids at the times and scales we now observe. The method is as systematic as it is ambitious. Researchers start from conditions inspired by the cosmic microwave background, tiny density variations imprinted at 380,000 years after the Big Bang. They then adjust these starting points: slightly higher density in one region, slightly less in another, differences in the properties of dark matter, or varied rules for star formation. The machines evolve these seeds forward across billions of simulated years, producing galaxies, clusters, and voids. Every run carries the laws of physics to their limits, playing out alternate histories at speeds millions of times faster than real time. The simulated universes can then be compared with Webb's deep fields, with DACY's measurements of galaxy clustering, or with the latest ACT and SPT cosmic microwave observatory results. Agreement signals that our models rest on firm ground. Disagreement forces a search for what is missing. The scale of these calculations marks a dramatic change from only a decade ago. Early simulations of structure often treated dark matter as smooth particles and baryons, as simple gas clouds. Today's exascale machines can follow entire cosmological volumes while tracking fine-grained feedback processes like radiation from massive stars, blast waves from supernovae, or energy outflows from supermassive black holes. These details, known as subgrid physics, play a decisive role in how galaxies form, yet they are too complex to model directly at every scale. So researchers design approximate rules for them, now refined with every new dataset. For example, groups are experimenting with higher resolution modeling of starbursts and active galactic nuclei to test whether such processes could accelerate early galaxy growth. The effort continues across dozens of teams worldwide, but so far, no single simulation reproduces both Webb's bright, early galaxies and the candidate large-scale voids at the same time. It is still an ongoing research problem. Even so, the progress is remarkable. The Simons Observatory in Chile, DACY in the United States, and both ACT and SPT have provided independent maps of large-scale structure and background radiation. These datasets constrain initial conditions so tightly that simulations cannot simply make up early voids or galaxies wherever they wish. Instead, they must grow consistently from the ripples seen in the CMB. That consistency is both a strength and a limitation. It ensures simulations track the observed universe into the present day with impressive accuracy, but it also reveals where they fall short. Given those CMB ripples, even exascale systems cannot produce, on their own, both the early order and emptiness Webb observes. Known laws set against known starting points do not lead to the reported outcome within the first billion years. Feedback processes illustrate this tension clearly. Stars form, radiate, collapse, and explode, returning heavier elements and heat to their surroundings. Black holes draw in gas while ejecting violent outflows of energy. These processes should slow down the rate at which galaxies assemble. Yet Webb consistently finds galaxies with billions of stars already shining when the universe was less than 500 million years old. Simulations that weaken feedback to allow such early growth run into trouble later, producing galaxies that are too large and overabundant compared to what telescopes see in the nearby universe. Simulations that strengthen feedback to match local galaxies cannot reproduce Webb's early ones. The balance point remains elusive, exposing a tension between past and present that theory struggles to resolve. The story is no better when considering voids. To form immense empty regions so early would require matter to fall away from those spaces and into surrounding filaments at a staggering pace. But gravity, gas cooling, and particle interactions place limits on how quickly matter can collapse. Push models too hard and the structures fragment unrealistically. Allow collapse to proceed at normal rates and the voids fail to appear. This is why simulations repeat the same pattern. Galaxies arrive too slowly, voids emerge too late, and the combination Webb presence is missing. The outcome cannot be dismissed as numerical error. It reflects genuine constraints from the physics we know. The sheer quantity of data now compounds the challenge. Webb's deep fields contain terabytes of information about faint galaxies, dust, and star-forming regions. DACY adds vast catalogs of galaxy clustering across billions of light years. ACT and SPT supply detailed maps of primordial ripples. Feeding these into models requires storage and computation on scales never attempted before in cosmology. Exascale hardware can rise to the challenge, but even it grinds under the need to compare thousands of runs against observed data. Quantum computers have been suggested as partial solutions, especially for testing exotic dark matter interactions or probabilistic field behavior. Even they, however, cannot yet bridge the gap between simulated universes and the cosmos Webb sees. The paradox is that the stronger these machines become, the sharper the mismatch grows. Lesser computers might have left wriggle room for doubt, but the precision of modern exascale runs removes ambiguity. When entire universes are evolved under well-understood physics, the predictions can be compared point by point with the observed record. Galaxy counts, brightness profiles, void statistics. Again and again, the simulations refuse to line up. What computers teach us, therefore, is not that physics fails everywhere, but that it fails in specific, critical places. Early galaxies too bright, voids too deep, structures too soon. This insight reframes the role of supercomputers in cosmology. They are not a guarantee of answers, but a tool for exposing limits. A weaker simulation might give the illusion of success by hiding flaws within approximations. Exascale runs cannot hide them. Limitations stand out, and inconsistencies repeat no matter the settings. Researchers cannot escape the conclusion that when galaxies shine prematurely and voids open vast emptiness, something in the model is missing. The machines bring this into stark view, sharpening the mystery rather than solving it outright. For viewers, the takeaway is simple. Computers are essential, but they also show us where existing physics might be incomplete. They sharpen the mystery rather than solve it by themselves. At the center of this problem lies a deeper question. How can evidence from CMB maps, galaxy surveys, and Webb's deepest fields all be correct but incompatible under current theory? Simulations only heighten the contradiction. They confirm that inputs from the microwave background align perfectly with local galaxies, yet they cannot stretch that harmony across the earliest billion years. Instead, they reveal a divide, a universe well understood in its middle age, and a universe still puzzling in its youth. As new simulations press forward, researchers hope refined subgrid physics, better data from ACT and DAISY, and expanded Webb surveys will eventually bring clarity. Perhaps minor corrections in how feedback operates at high redshift, or new knowledge about dark matter interactions, will close the gap. Or perhaps the constant mismatch will cement the need for undiscovered physics. Either way, the role of these machines stays the same: to mirror reality with precision, and where reality and law diverge, to highlight where our maps no longer match the territory. That is why the next step in the mystery feels larger than any single theory. Galaxies brighter than expected, voids wider than predicted, horizons that limit what we can see, and supercomputers that show equations breaking. It all points to a picture that escapes order too easily. The more detailed the search, the more often the universe refuses to align with the expectations laid out for it. A universe that defies its maps. When astronomers turn from theory to Webb's earliest deep fields, they find themselves confronted with a universe that does not match its maps. This is the landscape of a universe that defies its maps. On one side are candidate voids, stretches of space in epochs when matter was expected to be distributed evenly. On the other are galaxies already forming with surprising mass and brightness, their structure far ahead of schedule. Instead of a cleanly staged rise from uniformity, the observations suggest imbalance, emptiness alongside unexpected abundance. This is the tension now at the center of modern cosmology. Against this, the background radiation has long stood firm. The cosmic microwave background, especially as mapped in exquisite detail by Planck and in more recent refinements by ACT and SPT, shows only the faintest ripples in density, variations measured at a level of just a few parts in 100,000. These data confirm that Einsteinian gravity and the Lambda framework describe large-scale structure with remarkable accuracy. Surveys such as DAISY and the upcoming Simons Observatory reinforce this view, mapping galaxies and clustering across vast distances in a way consistent with the same model. Taken together, these results leave the large-scale picture intact. The universe is expanding, dark matter dominates structure, and dark energy accelerates the overall growth of space. In broad terms, the maps still hold. It is at the finer level within the first half-billion years that the maps falter. Webb's detections of bright early galaxies suggest more rapid assembly than expected. Reports of candidate primeval voids point to larger empty zones than theory allows. None of these overturn lambdactum at its foundation, but they do stress its predictions in the small-scale regime where galaxies, feedback, and baryonic physics matter most. That distinction is crucial. Cosmology is not being discarded. It is being tested in its strongest form by data arriving from a telescope built specifically to press against its boundaries. Dark matter lies at the center of this puzzle. Standard lambdactum assumes cold dark matter, creating smooth scaffolding for ordinary matter to collect upon. If the scaffolding was uneven, perhaps some halos formed unusually early while other regions lagged, leading to the simultaneous presence of bright galaxies and apparent emptiness. ALMA's recent submillimeter work, tracing ionized carbon emission around quasar hosts, confirms that massive halos were already in place less than 1 billion years after the Big Bang. This suggests dark matter was present and influential, yet does not explain why galaxies appear so mature in some places and absent in others. The contrast indicates that either star formation was extraordinarily efficient in select halos, or that subtler dark physics is at play. Modern simulations sharpen the contradictions rather than erasing them. Exascale computing allows researchers to evolve billions of particles under known physics, expanding fluctuations from the CMB into webs of galaxies. But so far, no model simultaneously produces both Webb's early luminous galaxies and voids of comparable size. Runs that generate rapid early galaxies often overproduce stars at later times. Runs that carve large underdensities too soon fail to deliver the luminous systems within the same epoch. Either way, the result is imbalance. The simulations confirm that standard physics can come close, but never align with both sides of Webb's discoveries at once. For researchers, this is less a crisis than an opportunity. Large-scale surveys like DAISY confirm that lambdactum describes clustering up through billions of years with excellent precision. Polarization measurements from ACT and SPT constrain the early density field with high confidence. These anchors are secure. Webb now adds a scale of scrutiny where discrepancies appear, forcing deeper work on galaxy physics, feedback mechanisms, and the behavior of dark matter in extreme conditions. In this sense, the universe is not broken. Our models are being stress-tested in the deepest way possible. The caution comes from consistency across instruments. When Planck, ACT, and SPT describe the early fluctuations one way, and Webb reports luminous galaxies and possible voids far earlier than expected, the contrast cannot be dismissed as a single error. Instead, it highlights a junction where knowledge thins. Each dataset remains individually robust, but stitched together they require refinements theory has yet to provide. The lesson is that cosmology is not a solved puzzle but a living one, where each new piece either locks into place or refuses to fit cleanly. Einstein's presence lingers in this debate. His prediction that beginnings would be concealed by both silence and horizon gains resonance here. The underpopulated fields recall the silence of epochs before starlight, as though their signals remain dimmed by ancient boundaries. The accelerated galaxies recall the horizon, where time appears compressed and structures arrive earlier than anticipated. Webb does not prove or disprove Einstein's caution, but it ensures that every interpretation passes through the filter he established a century ago. Physical law will not yield its earliest moments freely. The open question, then, is whether Webb's results point to missing astrophysics, refinements in dark matter modeling, or the onset of new physics altogether. Scientists emphasize the first possibilities most strongly. Feedback from massive stars may act differently in high-density conditions. Black holes may have seeded more rapidly than assumed. Star formation itself may proceed with efficiencies we have not correctly modeled. Each of these is now being programmed into simulations and tested with further data. Radical departures, such as novel dark matter particles or altered early vacuum physics, remain speculative but are not entirely dismissed. To sort among these ideas, scientists are pursuing concrete next steps. Spectroscopic confirmation of high redshift candidates is being prioritized, since photometric estimates alone can misclassify galaxies. Targeted gravitational lensing studies of candidate void regions are underway, designed to determine whether unseen halos lurk within them. Ground-based projects like the Simons Observatory, along with ongoing ACT and SPT campaigns, continue to refine polarization maps of the CMB, sharpening the baseline for structure formation. At the same time, new generations of supercomputer simulations are being built with higher resolution and more detailed prescriptions for feedback. These 4 parallel tracks define the practical path forward. Each seeks either to resolve Webb's tensions within lambdacdom, or, if necessary, to highlight where the existing model must be supplemented. Taken together, the evidence leads to a humbler vision of cosmology. The large-scale scaffolding of the universe remains well explained. The expansion of space, the presence of dark matter, and the role of dark energy in accelerating growth are secure results. But the fine-grained history of galaxy birth and void development may require either substantial correction or new layers of description. In this liminal space, the promise of mapping origins collides with the reality of unyielding anomalies. What emerges is not simply a breakdown, but a recognition of how cosmology operates at its edge. Maps are always provisional, valuable until new light reveals their limits. Webb, ACT, SPT, and DAISY together mark the most refined maps yet, but they also show how narrow the corridor becomes near the universe's beginnings. This is precisely where Einstein warned that our view would blur into uncertainty, and where today's contradictions take their most challenging form. The story does not end here, though. With deeper spectra, wider surveys, and ever larger simulations, scientists continue pressing forward. Each improvement promises sharper clarity or sharper paradox. That is the rhythm of cosmology. And as new results arrive, one fact remains. The closer we come to the edge of our maps, the more the universe forces us to confront its limits. That tension defines the next question, a question that lingers just beyond the science itself, waiting at the boundary of what can ever be known. Webb's discoveries now stand at a crossroads where Einstein's predicted limits, the CMB's smooth order, and the telescope's surprising galaxies and candidate voids all converge. Together, they reveal both the strength of current cosmology and the strain placed on it by the very data meant to confirm it. We don't yet know whether these early void-like regions confirm Einstein's caution or point toward new physics, but they guarantee that the next decade of astronomy will be decisive. Science advances by confronting contradictions. Stay with us while astronomers test, simulate, and argue their way to better answers. If you want breakdowns of the follow-up studies and the best confirmed results as they arrive, hit subscribe and tell us which part of this mystery you want explained next: galaxies, dark matter, or the CMB.